Let me hit save. And again, I'm just filling the air so that I can get my audio feedback so that I know that it's working properly. Get attendance. And what today? I'm gonna shut that down. We had done there. Let me check attendance once more. Let me see. Chat. So there was a request to go over some homework. First, we need to do the lecture, and then we can go over homework, right? I know the last class, I got stuck on the very last question. As soon as I let you guys go, it like clicked in my mind. So I found what I needed to kind of get to the bottom of it. So I did a couple of examples of that second derivative of the implicit differentiation. So we can talk about this. Let's get to the lecture for today. And then on the back end, we can kind of hang out on the back end as long as we need to, as long as we can, and work some problem sets. But we definitely got to do our business first. Like get down to business first. So let's share the screen. Come on. These updates. And so now it's kind of like throwing things. There it is. Okay. Start the broadcast. Now responsive, but that's okay. All right. So as usual, let me see. So we're in the home stretch, gentlemen. Let me just kind of take a moment to think about, and I'll check attendance again and right in about 5.5 minutes. I don't know what week this is. If last week, let me see, this is the first week, the second week after spring break. So spring break was like week 8, that was 9. So this should be the top of week 10, right? So we have 6 sections remaining, 4.1 through 4.6, right? 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, right? Once we get to 4.6, that'll be the last of the new material. And then, we'll take exam 2, and then we'll be getting ready for our final. So exam 2 will be over chapters 3 and 4. We just finished chapter 3 on some applications on differentiation. So with this chapter's on chapter 4, and now, which is integration. And so to me, like, this is one of the more important concepts we needed to touch on. And so that's because we needed to kind of get to this chapter. That's why we had the rhythm that we had. Sometimes I know we were doing 2 sections a day, and I know that was intense. I tried to lighten the load by like assigning less work, but the whole point was to get to this chapter, because there's no other class where you take the time to go through this material the way that we do here. But going forward, if you take any math class above this, I mean, the stuff that we talk about is kind of like, I don't want to say it's not second nature, but everybody uses it. And the more you do it, you'll start to see it is a little bit intense the first time you see it, but if you just keep trying, keep practicing, keep getting your reps in, I want to say it gets a little bit easier. It does get easier. Like, the only reason it gets more challenging because you take those concepts and you apply them to other things, right? So you just kind of keep using the concept and then you'll get it. And so what we're doing here with this chapter in chapter 4, so what we've been doing all this while, we've been, taking a function, we take the derivative, we get an output, right? And the derivative basically is giving us the slope of the tangent line at a point. So now what we're going to be doing in chapter 4 of integration, suppose you're given the derivative and you want to work backwards, right? So we're going to see how to undo these derivatives, right? Given a derivative, how do we undo it? Okay, so that's the premise. That's the baseline of what we're doing. Okay. Let me back up a little bit. Go here. That's better. Okay. And again, I'll check attendance in right at about 3 minutes. Okay, so we're moving into chapter 4 on integration. If you're still here, you're still hanging strong. Even if you're not here, I'm proud of you. I know this stuff is intense. We're remote. It's not easy, right? But if anything worthwhile in life were easy, everybody would be doing it, right? Anything that's worthwhile generally is never easy, generally speaking. Obviously, there's going to be some exceptions to the rules. Okay, let's keep going. Just hang strong. I know you can do it. Okay, so we're moving into section 4.1 on anti-differentiation. A few objectives. We like to find an antiderivative of a function, evaluate indefinite integrals using basic rules of anti-differentiation, and use initial conditions to determine an antiderivative. it probably would be better if I looked at these in advance, but again, I generally don't. So, it might be a little bit choppy, but we'll get through it. So theorem 1, the antiderivative of f of x is the set of functions, capital F of x plus c, such that d by dx, let's grab this guy. Ooh. Hopefully you have enough of a charge. Such that the derivative of our antiderivative is our original function. All right, so the constant c is called the constant of integration. So once we start, evaluating or finding these integrals, the way you check that you have the proper integral is you take the derivative. So whatever answer you get, when you take the derivative of it, it should give you what you originally started with, right? Okay, let me see the time. I need that to, okay. Yeah, that's a little over a minute. So integrals and integration, antidifferentiating, I can't even get the word out. It's often called antiderivative of x squared is x cubed over 3 plus c. We write the integral of x squared dx is x cubed over 3 plus c, where this notation is used to represent the antiderivative of f, right? So this, usually we read this as the integral of f of x dx. More generally, the integral of f of x dx is f of x plus c, where f of x plus c is a general form of the antiderivative of f of x, all right? So when we integrate, there's going to be some constant of integration. And you'll see it, you'll see why. Like it'll start to click as we start to work a few examples. Okay, so let me see. Let me finish this one, then I'll check attendance. So with this example here, let's just check it, because the more people I can get in on this, the better. I think attendance looks good, so I'm not going to worry about that. These indefinite integrals, that is, find the antiderivative of each integrand. All right. The answers are already there. I didn't even realize. Okay. Tag on it. I thought I got rid of them, but I got rid of the wrong thing. Okay. Well, let's do this then. I know you can see them, but we're gonna have to go with it. Let's copy, paste. Let's try. Let's see. Like talk through it to give you some of the copy. I'm gonna work backwards. All right, we didn't really want the answers. Okay, so let's try this. This is one. So the integral of 8 dx, right? So you ask yourself, like, what's the derivative? Like the derivative of what is 8? So that's like one of the more simple ones. So we would say what, 8x plus c, some constant, right? Because if we take the derivative of 8x is 8, and then the derivative of a constant is 0. So that one. Okay. Okay, so we'll start to see where, for instance, this 3 can essentially go in front, right? You can almost ignore that 3. And for instance, if we're integrating x squared, right? And we'll talk more about this momentarily, but the integral of x squared, you basically, when we take the derivative, we subtract 1. So when we take the integral, we're going to add 1. This is going to become x cubed, and then we divide by 3, all right? So this is going to be 3 times x cubed over 3 plus some constant of integration. And then these two guys cancel each other out with x cubed plus c. And again, we know that this is true. Again, if we take the derivative, what's the derivative of x cubed? The 3 comes down and we subtract 1, so we get 3x squared. You see it right here. And the derivative of a constant is 0, so that guy's going to go away when we take the derivative. E to the x should be itself, right? Because here, it should be e to the x plus some constant. Because the derivative of e to the x is itself, and then this is going to go away when we take the derivative. Natural log, is that right? Plus some constant. because the derivative of natural log is dx by x, which is what you see there. Okay. I think we already had these. And again, we check by just take the derivative. We got this answer, we check by taking the derivative, right? And they all work out. Wow. We check the attendance, okay. So we got this theorem 2, we got this basic integration formulas, right? Okay. So the integral of a constant, if we're trying to undo a constant, that's going to be that same constant times x, right? So I think this was the very first one we did where we had the integral of 8. That was the same as 8x because the derivative of 8x was 8, right? And then x to some power r, this is the one that I did that I didn't really explain. This was the second one. So we have x to some power, the integral of that is going to be x to that power plus 1 over that power plus 1 plus some constant, right? So this is, and it looks intimidating initially, but again, as you work a few examples, these kind of sink in, you know. And I mean, they can get a little bit funky. Just keep trying. As long as you keep trying, you'll get it. To integrate a power of x other than -1, increase the power by 1 and divide by the increased power. Okay. So then now, for instance, if we're doing x to the power of -1, that's the one where we had basically it was dx over x. So the integral of dx over x is natural log. That was a special case when we have x to the power of -1. Positive, where the base is positive, then this stuff holds. If that base is negative, if x is negative, then we have to say it's going to be the natural log of absolute value of x. X is positive though. That doesn't generally happen where x is that base is negative. Let's see. So e, the integral of e is going to be itself divided by that constant, right? The constant in the exponent. So this constant, again, these constants can kind of go just in front. The one for e, you got to divide by that, right? And again, if you don't divide by a, the way you'll catch it, like suppose you just integrate it and you put be to the ax and you didn't put this a, suppose you didn't put that. When you go to take the derivative, you're going to have an extra term in there, right? So if you start with just e to the ax and you take the derivative, then you're going to have an extra times a term. So to get rid of that times a, you divide by e, right? It's a little bit like this. Like, let's just keep trying and we'll see it. So use the power rule of antidifferentiation to determine these indefinite intervals. Okay. So the first one, x to the 7, we add 1. So it's going to become x to the 8 over 8. So then a is going to be x to the 8 over 8 plus some constant. Let's go ahead and do b. X to 100 over 100 plus some constant. For half, right? So let's do the same thing. Square root of x is the same as x to the power of 1/2. So if we add 1 to 1/2, we get x to the 3/2 over 3/2 plus some constant. I'm gonna just leave it like this because we could flip and multiply right as a radical expression. I'm just gonna leave it like this. Then d, I think d is fine. So then that's the same as x to the -3. If we add 1 to -3, it's going to become x to the -2 over -2 plus some constant. Okay, let's see how do we do, and then we can assess. Wait, so I guess I didn't need that slide. Let me get rid of that slide. Delete. I think we got this, x to the 8 over 8 plus some constant, because again, if you check by taking the derivative, you get back to x squared. We got x to the 100 over 100 plus a constant, and we got that one as well. Up here, we got x to the 3/2 over 3/2 plus some constant, right? So we got the same thing. You should just check by taking the derivative. -2 over -2, right here. Yeah, x to the -2 over -2, when you, right here, you see it here, and then when you simplify, it gives you this. this is not clear, just stop me. We're actually moving at a pretty decent pace. We are just about halfway through this, and the quick check will get us past the halfway mark, right? Because again, I usually leave these as exercises, you know. And so we'll get to the lecture, and I know there was a request to go through some homework questions, so I'm eager. Let's do it. But let's finish this out. Determine the indefinite integral. Okay, so E. Now let's try this one, right? So let's start with the copy of the original. Integral of e to the 4x dx. Okay. Now I'm tempted to do just write it itself, e to the 4x plus some constant. But if we go to take the derivative, we're going to have times 4, so that means we have an extra term. So we need to divide by 4. Okay. So now when we take the derivative, when we multiply by that 4, they cancel, and we finish with this guy. Four plus c, right? We know that d by dx of e to the dx is itself. It's reasonable to make this initial guess, right? This is what we were saying. But if we take this derivative, we get an extra term, right? So the derivative of this guy is right here. But this 4 is an extra term. So to get rid of that, we divide by 4. So we modify our guess by inserting a 1/4. So then the integral of e to the 4x dx, now we're going to modify our guess and say e to the 4x over 4 plus a constant. Now when you take the derivative, you finish with the proper result. I'm going to leave this as an exercise. Zoom really quickly. Good, and there's something going on in the chat. Let's keep going. So we have this theorem 3. So properties of antidifferentiation. The integral of a constant times the function dx is like, this is what I was saying before, where we can essentially factor out that constant, we can just move it to the front. You see it here in front. So the integral of a constant times the function dx is the same as the constant times the integral. So it's like we factor out that constant, move it in front. The integral of a constant times a function is the constant times the integral. The integral of a sum or difference of functions is the sum or difference of the integrals. The integral of a sum or difference is the sum or difference of the integrals, right? So it's almost like we're distributing the symbol, you know, across addition and subtraction, but essentially we're just breaking it apart. Okay. Definite integrals, assume that x is positive. Okay, let's start with A. I'm not going to write the original. So we could break these apart into 3 separate integrals. I'm just going to work them each individually, right? So x to the 5th, we add 1, it's going to become x to the 6th. So that's going to become 3x to the 6th over 6 plus 7x cubed over 3 plus 8x plus some constant. And then we simplify these. To the 6 over 2 plus 7x cubed over 3 plus 8x plus c. If anything is not clear, we need to go back. One or two things, either we get it, I guess we can throw a third option in there. Either we get it or we don't get it, or we're still processing. Okay. I am tempted to distribute. Since we're dividing by a monomial, we can kind of distribute, right? So this is going to be the same as 4x to the minus 1 plus 3 plus 2x cubed. In the integral yet. Come on. Of that dx, okay? So then that's going to be, now remember we said that negative x to the power of -1 was a special case, so that one's going to be natural log. 4 times the natural log of x plus 3x. That becomes x to the 4. X to the 4 over 4, but then 2 over 4 reduces down to this, plus c. 2, 7/3x cubed. Okay, we got the first one. 4 natural log of x plus 3x plus x to the 4/2 plus c. Okay. There, having fun out there. Also, as a reminder, so with all of our assignments on Pearson, remember we get unlimited attempts. Anything that's on Pearson, you can still work on it. You can still earn up to a 90% on any assignment that's there. Only reason you really don't get an A is you just didn't like go for it. Like if you just go for it, you can do it. We still got a full month, right? Because the month of April, but then as soon as we move into the month of May, we're going to be going into finals. So you have the full month of April to kind of get it in order. Okay. Leave the quick check as an exercise. Let's give this one a go. We're almost there. This went a lot faster than I anticipated. That's okay. So find a function such that f prime is this and f of -1 is this. Okay. So if they gave us f prime, let's integrate to find the antiderivative, right? So we want to find the integral of x squared dx, right? That's going to be x cubed over 3 plus c. Again, this is we're going to call this our capital F of x, right? And then they give us that f of -1 equals 2. So we can say f of -1 being this -1 cubed over 3 plus some constant, that should equal 2, right? So when x is -1, y is 2. They gave us a point so that we can solve for c. Left and right, what is this? That's going to be a -1/3. So just add 1/3 to both sides. C equals 2 1/3. 3 times 2 is 6, 7/3. So our f of x looks like it's going to be, again, the capital F of x is just general antiderivative. And then we get to the specific one because they gave us a second point. They gave us more information about our function. So then our f of x should be x cubed by 3 plus 7/3, right? Let's check. Again, something like this. -1, right? This is going to be a -1/3 plus 7/3 give us 6/3, which is 2. And then if we take the derivative, the 3 comes down. We're going to be left with x squared. And then this goes to 0. This term goes to x squared, right? Which is what we want. So then this is it. X cubed over 3 plus 7/3. Okay, that wasn't too bad for an introduction. So for a section summary, the antiderivative of a function is a set of functions d by dx. This is the general form of the antiderivative, such that d by dx of the antiderivative equals f of x, where the constant c is called the constant of integration. An antiderivative is denoted by an indefinite integral using the integral sign, this guy. If the antiderivative is an antiderivative of f, we write the integral of f of x dx is f of x plus c, right? We check the correctness of an antiderivative we have found by differentiating it. Okay. The rule of antidifferentiation, the integral of a constant is going to be basically constant kx plus c. The power rule, the integral of a power is going to be x to that power plus 1 over that power plus 1 plus c, right? Again, where that power is not equal to -1. The natural log, if that power is -1, then if it's like x to the -1, that the integral is going to be the natural log. And then the integral of e is itself divided by that a that you see there, right? Is an ordered pair that is a solution of a particular antiderivative of an integrand. So this last statement is basically referring to that last example that we did, where we found an antiderivative, then they gave us like some more information about the original function so we can get to the specific function, okay? I think that actually gets us to the end of this section. So I know that there was a request for homework. I don't know, like, have you, if you can like go ahead and do the either ask my instructor. If it's a homework question, you can use the ask my instructor. That's the best way. That way I can pull up your specific question. If it's a quiz or an exam, then we'll just kind of go back and forth until we get it. These guys. Let's go to edit. So let's go. Well, we're not done, but
Professor, what'd you say again?
I know you have requested to like, so we can pull those up.
Okay.
Like if it's a homework question, the ask my instructor is the best way to do it. If
Yeah,
it's like a quiz or an exam, then we can.
I sent it to you. Do the homework.
No, when was it? Like a few minutes ago, or like days
Yeah, it's
ago?
probably like 5-10 minutes ago.
Okay.
I can send it again if you need me to.
No. Let me do like this. It's gonna be here. Okay, let's pull up. Switch these up. Machines, operator's efficiency changes with respect to the time is given by this, where this is the number of hours the operator's been at work. Find E of t given the operator's efficiency after this, that is E of 2. E after 3 hours, okay. T of this. Well, this is the number of hours that has been at work. Find E of t. Is this, let me see, what section is this from?
You said what section?
Okay, this is from this one. Okay, cool.
Yeah.
Let me pull it up. I will take this. I'm gonna go from here. I'm gonna take these guys. Actually, let's trash this. Give me just a moment. Zoom in. It's better. I know it's better. All right. Okay. Let's copy. I'm gonna add a page. And let's paste. Come on. Paste. And let's crop. I know you can't see this yet. Let me come back. And like that. And like this. And okay. Zoom. Let's share the screen. Okay. All right. So this was the first one, right? It says the rate at which a machine operator's efficiency E expresses the percentage changes with respect to the time is given by this. So they give us a derivative. They want us to find the original function where t is the number of hours it's been at work. So find the original function. So basically they're asking us to integrate, right? So the integral, why does it look like that?
Hey, Professor, I don't think your screen is actually showing.
Okay. Like this.
It says you started it, but it's just blank still.
Let's try to get this screen. Start the broadcast. You see now? Are you able to see it?
Yeah, I can see it now.
Okay. So let's see. It looks like they're asking for, why is it keep doing that? I think what I need to do is like this. Try this for like a second or two. Okay. So it looks like they're asking for, this stuff is on the front. Hang on. That's better. So the integral of 30 minus 8t. That's so irritating. I don't know why it's doing that. I think it's doing, I think the battery might be low. Let me just give it a few seconds. So this is what we literally just talked about just now. This is why I was like, I wanted to go through the lecture first because we had, we did just finish the lecture. Let's try this one more time. So then, that's fine, dt, right? This is what they're asking us to integrate, right? So this is what we just talked about. So then again, you could just break these apart. The integral of 30 is just gonna be 30t minus 8t squared over 2, right? And then plus a constant. Let me see, they should give us a point. Fine, given that the operator is efficient after 2 hours is 77%. So that's E of 2 is 77, right? So when T is 2, the efficiency is 77%. So then that they give us that so that we can solve for C. So then we would have what, 30 times 2? 8 divided by 2 is what, 4? So 4 times 2 squared plus C equals, so when T is 2, the output is 77. So now we can solve for C. C is going to be, what is that, 77 minus 60. 4 times 4 is 16, so minus 16. 17, and then 7, looks like, is that a 1? It looks like it's 1, all right? So then it looks like E of T should be 30t. 8 divided by 2 is 4, so minus 4t squared plus 1. Oops, plus 1. Right, and then we can check. Okay. Nope. Right, so this is the application of what we spoke on today. Okay. So then, like for instance, when we take the derivative, we should get 30 minus 8t. So the derivative of this guy is 30. The 2 comes down. We get minus 8t, and then this guy goes to 0. Right. So when we take the derivative, we get the proper thing. And then also we want to check that when we plug in 2, the answer should be 77. So then 60 minus what, 16? Sorry, think about this. Let's see. So 4 times 4 is 16. 60 minus 16, 60. No, something's off. What are we missing? Let me see. 76. That's a positive 1. Oh, I see where I made my mistake. Right here. Right here. I switched the sign. So this was a 60. This is supposed to be a minus right here. Let me do it right. This is supposed to be minus, right? So then with that being a minus, 77 minus 60, and then it's supposed to be a plus 16. That's where it's getting off. And the reason we caught it because we checked, right? So then that's what, 17 plus 16, 33. So it looks like this is supposed to be 33. That's a 17, 12, 13, yeah, 33. Okay. So now let's check again. Again, now when we take the derivative, we get the proper derivative again because the constant goes to 0. So we get this guy. And then we just need to make sure that when we plug in 2, we get 77. So this is 60. For minus 16 plus 33, right? 60, 50, 44 plus 33, 77. Okay. So I feel good about this answer for part A. Okay, and then use the answer in part A to find the operator's efficiency after 3 hours and after 5. So then if this is correct, then you just plug in when T is 3 and then when T is 5. Let's just go ahead and do it quickly. But this was part A. So then they're asking for E of 3. Let me see. That's going to be 90. 9 times 4 minus 36 plus 33. So that's minus 3. So then that's what, 87. And then they want an E of 5. 150. 25 times 4, so minus 100 plus 33. What is that? 50 plus 33 is what, 88? Okay, so these are the results to read that. And then I'll do copy and paste. Okay, and I think I have the results on the previous slide. We got, okay, they got 33 plus 30t minus 4t squared, and then 87 and 83. You got that last one wrong? Oh, no, that's what you answered. No, I think, okay, let me go back to see. Yeah, that should be 88. I think that's what you answered. Let me see. You answered this, okay. So 83% is correct. So we got the rest of it. Why are we getting that one wrong? Some calculation wrong. Let's look at this again. That's 50. Oh, 83. Duh, I don't know why I kept wanting to make that be an 8. Anyway, so this is it. Sorry for that one. Okay, hopefully that cleared it up. Let me pull up the other one. I'm gonna hop over here. Let's hit stop the screen share.
Yeah, it cleared up. Thank you.
Okay. Yeah. Yeah, we'll do a breakout room if you need to talk privately, kind of closer towards the end. And we have about 30 minutes. Let me pull up this other one. And if you have more, you can just again just do the act structure. We kind of keep it going. I see you sent another one. I'm pulling up the second one that you sent. Given this, find d by dx. Let me see. How did I do that last time? I think if I zoom out, zoom in. That's weird. I don't know how I did that last time. If I go here, 4.1, so the same section, that's fine. Let's just get a copy of this. Given this, find d by dt when y is this and dy by dt. Let me think about this. So the derivative of x with respect to t. Okay, I think, let me think about this. They give us dy by dt. Okay, let me go to view an example. So given this, use implicit differentiation and differentiate each term with respect to t, treating y as differentiable functions. Substitute the value, that's fine. Okay. So dy by dt equals this. Okay, so then you integrate. So use this equation to determine, first find the values of x using this equation. Dy by dt, how did I used to do these? Dy by dt is this, and dx by dt is this. Let me think about it. Implicit differentiation, that's fine. And differentiate each term of the equation with respect to t. Treating y and x, So use this equation, substitute the given values into this equation and solve for dx. So we have y equals this, right? So then if we take the derivative, so we're taking the derivative with respect to t, that 1/2 comes down, right? Okay, with respect to t. So, okay, I get that. Then use this equation, that's fine, to determine dx when y is this, so you basically plugging all that in. Okay. Let me start by here, let's do this. So let me bring the image back up, share the screen. So this one is a play on like implicit differentiation, right? Let's start here before we kind of work ours. So this example, let me just start over. I want to view an example. Here it is. So let's start here with a view an example, right? So it says given y equals the square root of x, we're asked to find dx by dt when given these conditions. They give us y and they give us dy by dt, right? So if we start with that y equals the square root of x, we're gonna take the derivative of both sides with respect to t. So we're basically finding d by dt of the left and the right. Now I know there's no t there, but you basically just take the derivative like normal. Like for instance, the derivative of y with respect to t is going to be dy dt. The derivative of x with respect to t, you basically take the derivative like normal. You just need to add on that part that says dx by dt. So that means we know that we're taking the derivative of these with respect to t, right? I feel like that's what I feel like I got what I need. So let's take ours and I'll show you how to apply it to yours and we'll see if we can get it. Yeah. And it comes to 3.9, that's fine. Okay, so let's go like this. Let's get a copy of this. We'll go find dx by dt. Let's start here. So we're gonna take, come on. Right here. Okay. Okay. So with this one, let's start here. Now we have this y equals the square root of x, right? Let's take the derivative of each of these with respect to t. So the derivative of y is just going to be dy dt. So it just means we're taking the derivative of y with respect to t. The derivative of the square root of x with respect to t, you just take the derivative like normal. So that 1/2 comes down. We get x to the negative 1/2. But then we need to identify that we're taking the derivative of x with respect to t. All right, so these are all the parts. So they're asking us to find this guy that's in blue. And then we're just basically going to plug in what they give us, right? So let's see. We might come back to that. Let me see. They give us dy by dt. We might be able to solve for x. Let me see. Because they give us dy by dt and they give us y. I think we can solve for x and then use that x here, right? So the left part they gave us, let's go ahead and see if we can solve for x. I think this, let's just try it. I'm not 100% sure, but I have a hunch, right? So again, this guy is right there, right? But then they give us y equals 2. So let's use this to see, can we solve for x here? Okay. So then we have 2 equals the square root of x, square both sides, what? X equals 4, right? Okay, let's see if that works. So now if we plug these pieces in, dy by dt is 1.75, 1/2, yeah, 4 to the power of a negative 1/2, and then we still have this dx by dt, right? So negative exponent moves that to the bottom. The square root of 4 is 2. So then we get 1.75, 1/2. So a half times a half is a quarter times dx by dt. And then ultimately, dx by dt basically multiplied by 4. Let's see. Hey Siri, what's 1.75 times 4? 7 times 4 is 28. 4 times 4 is 7. Okay. Oh, I don't know where I got 7 anyway. 7, right? So then we get 7. We can try it and see if it works. If it doesn't work, we'll go back and try to figure out what we're doing wrong, right? Okay. So, and I want to check one other thing before we submit this. I'm going to hop back here. Come on. All right, let's see if we do it here. Is that okay? I'm going to go to view an example. I just want to make sure that what we did was fine. We did that. We took the derivative. So we started with the y equals. We took the derivative of both sides with respect to t, right? Then we use that to determine, given this y. So first find the value of x using this equation, right? So let y equals 8. You square both sides, so then x should be what? 8 times 8 is 64. You see it there, x equals 64. Okay, so I think what we did was fine. So then I think we got dx by dt was 7. So let's just plug in 7. 7? Are you off? No? Why are you not responding? 7. Let's go like this. 7. Hang on, I gotta get my keyboard working. I don't know. This thing is always kind of tricky anyway. 7? No? Okay, maybe I can use this. 7. That was an adventure. I feel like we need to do another one of those. Let me know. I know you sent a third one. I'm gonna go ahead and pull that one up. You may or may not have gotten credit for that. I'm not really sure. It's okay if you did. If you didn't, we can get you squared away. Let's go here first. Stop the share. Let me pull up the next one. Did that make sense, or do we need to do another one of those, or?
No, it made sense. I wrote it down. I was just doing the last part wrong. That's why.
Did you see how I used the X my instructor?
Yeah.
Okay. Let's see this one. It helps when we did this one already. I think you sent the same one again.
Yeah, I think I sent it twice. I only sent 2.
Okay. Okay, so let me see the time. So what we can do, we can take the remainder time by going through as many of the other homework questions as we can. If I can, I don't know why my stuff is not responding. So let me pull up Pearson. Just go like this. My lab and mastering. I game too much, so then it's becoming less and less responsive. But I'm learning how to game around it. It just affects my game. Come on, sign in. We got let's do what we can in 10 minutes. We got about 15 minutes left in class, but let's do what we can. Let's get at least like 1 or 2 questions in. If I can get this thing to respond. Okay. Calculus. Let's go ahead and start sharing the screen. Start the broadcast. And with homework from last week on that very last question, I went back and I made a separate video for the implicit differentiation of the second derivative, because I know I didn't finish it, and so then as soon as I let you guys go, I was able to figure it out. And so I hadn't figured out how to put those two videos together, but it is there, and I just need to organize it and put it with the playlist. Right here, not the quiz. This is week 11. Yeah, right here. Antidifferentiation. Let's start with question 1, and then let's try to get at least like 2 questions from chapter 4. So this is like an older one, and let's zoom out. Hopefully my keyboard is working. I think it's been like
I sent another one.
Another one? Okay, let's pull it up.
If nobody else have any questions.
Right here. Pull it up. Let's hold off on 4.2 because we haven't talked about that yet. Approximate the area under the graph. So basically they're saying take the integral. So this is like this is a definite integral. You still integrate like what we were doing, but then when you get your answer, instead of putting plus c, you need to plug in, for instance, for yours, you're gonna plug in when x is -7 minus when x is -2. It's the same thing that we were doing. I think I'd rather save that for tomorrow though. It's not that much different than what we're doing now. You just take the integral like normal, but instead of putting plus c, you got to evaluate it. Basically, you plug in when x is -7 minus when x is -2. We're going to see that on Wednesday. I don't really go ahead. Let me get to the first question from chapter 4 here. Okay. And that's a quick one. Let's go here. I'm watching the clock. We got a solid 10 minutes. We got a little over 10 minutes, but I don't want to keep it more than 10 minutes. Okay. So this is question 6. This is the first one from section 4.1, question number 1. Find an integral. So this is the integral of a constant. So this answer, it should be like 11x, it should be like plus c. Let's see how it accepts it. 11x, let's do plus c. Okay, let's try another one. So this one, you add 1 to the exponent, it's going to be x to the 4 over 4 plus c. So this is one that we did today. X to the power of 4. Come on. Over 4. Why is it like tabbing? Man, that's just like on the first today. I see it wasn't doing this last time. You have to abandon that because that is getting in the way. Where's my keyboard? That's going to be just turn it. Okay. Plus C. Jeez. That was so much. Hopefully there's not a space in there. I think there's a space in there. That's why it's marking it wrong right here. But no. Shift plus C. Let's see. use it, yeah. I don't know. I'm gonna just enter. And that was the first thing that we put. I think it's just like let's just do another. I think it's just like the keyboard on the fritz. Okay, let's do like this. We're gonna say this one is x to the power of 9. Oh, here it is. X to the power of 9 over 9. There we go. Now we're moving. Plus, let's see. All right, that's better. Yeah, it was the keyboard was just on the fritz. Didn't make it work. Okay, same thing here, right? What's the time? Yeah, we just want to add one. So 7/6 plus 1 is 13/6, right? So this was going to be x to the power of 13/6. Yeah. 13/6. So over 13/6 is going to be 6/13. So it's going to be 6, 13, and then plus C. And if we need to talk about any of these or go back, just stop it. Hopefully you can see. Find the integral. I think this one is quick too, right? Let's see. So the x squared becomes x cubed over 3. Right? And the next one is minus. I surely was about to hit plus. So minus is going to be 5x squared over 2. So let's hit like this. That's 5x squared over 2. Okay. To the right. And then we're going to say plus 4x. 4x plus c. So we're just adding one to each exponent and dividing by that new exponent for these. Okay. So I think that's x to the power. No, that's 1 over, okay. That's 1 over x to the 6. So that's the same as x to the negative 6. So if we're starting with x to the negative 6 and we add 1, that's going to become x to the power of -5 over -5. We can just put the -5 here. That should be fine. Then we're going to say plus c. Okay. So we have the cube root of x to the 5th. That's going to be the same as x to the 5/3, right? So if we have x to the 5/3 and we add 1, that's going to become 8/3. So that's going to become x to the power of 8 over 3. Divided by 8 over 3 is going to give us 3. Here, let me see if I put the 8 up here. Yeah, 8 over 3, so it's going to be 3 over 8. Because we divide by a fraction, you flip and multiply. Oh, I forgot my constant. Yeah. Plus c. Okay. So the integral of e is itself. We're still going to have our e to the power of -9x, but then we need to include another -9 there. And we need our plus c. Plus c. See the time. We got a solid 5 minutes. Let's go for another 5 minutes. Okay, let's do the same thing here. So we got our fraction. The 6 just kind of persists. We keep our e to the power of -0.2x, but then we need to divide by -0.2, and we probably should simplify. Divided by -0.2. We're still going to keep our plus c. I'm going to submit this. If it's wrong, let's just go back and simplify. This 0.2 is the same as 2 over 10, right? So if you flip and multiply, so 30, negative 30, 2 over 10, you flip and multiply. That's 5 times 6. That's going to be a negative 30. Let me get rid of some of this stuff. I just want to get rid of the fraction. I didn't want to do that. Okay. I didn't want to get rid of all of that. So we said what, negative 30? Negative 30. I think we still had our e to the power of negative 0.2x, because we already divided by the negative 0.02. And then I think we still need our plus c. I think this is fine. Okay. The integral expand first. Okay. So I'm gonna take my notes here, right? If we expand that, first times first is what, 36x squared. Okay. 10 times 6 is what, 60? 60 up, what, plus 60x, and then plus 25. So that was just me expanding it. Now, if we take the integral of this, I'm going to write the answer, but no, I was trying to drop a line. I wasn't trying to submit that. It's fine. So I'll write the answer in front. So now when we take the integral, you know, x squared becomes x cubed over 3. So x cubed over 3, what is that, 12x cubed? 12x cubed, okay. 60x, so we're gonna say plus, the integral of 60x is 60x squared over 2, so that becomes 30x squared, 30x squared, okay. And then the last one, 25 becomes 25x. I'm coming back up, plus 25x, okay. We need to get rid of all of that and then put our plus c. Thank you, I know we're done. Stop. Oh, I hit snooze. Darn it. Clear. Hopefully that solved it. So getting rid of all of this, and we do a plus c. Okay. So we just we expanded it, and then we kind of just did what we've been doing, right? Okay. All right. I didn't really want to keep you past that point. I don't know if you guys have other questions, or if you want to keep working, we can. Okay. But if there aren't any, thank you. If there aren't any burning questions, we'll end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. Okay. So looking ahead with the question that I saw from section 4.2, it looks from the question that you sent me, it was pretty much the same thing as what we were just doing. Again, the only change is that whole, you got to evaluate it with those endpoints. You got to say one, you plug in one endpoint, whatever answer you get, you say minus whatever answer you get when you plug in the other endpoint. Okay, guys? All right. And on that note, we'll end the session here. And from one beautiful mind to another, enjoy the rest of your day. Okay, take care, guys. Peace.